Welcome everyone. We are starting Chapter 5, which is on analytical trigonometry. Many students will agree that this is the hardest part of pre-calculus. So look at it this way. We're doing it early in the semester so you can get it over with. Okay, this whole chapter, or rather the first half of the chapter, focuses on identities and proving things to be true, proving identities, proving statements, proving equations, if you will. Reciprocal identities. You pretty much already know these. We just haven't officially written them out as identities. What is sine? Sine is the reciprocal of cosecant, right? So we can go ahead and say sine of theta is the same thing as 1 over the cosecant of theta. What is the cosine of theta? Well, again, we already know it is the reciprocal of secant. So it's 1 over secant theta. May seem redundant why we're doing this, but again, we're going to use these facts in our proofs. Cosecant, again, is the reciprocal of sine. Secant is cosine. Cotangent is 1 over tangent. The two on the right are called the quotient identities because remember that tan and cotangent can be written as a quotient of two other trig functions. So tangent theta, of course, is sine over cosine, and cotangent is therefore cosine of theta divided by sine of theta. There we go. These next three identities are probably the most important identities other than the ones you already know above, the reciprocal and the quotient identities. You absolutely have to know these. They are critical when simplifying trigonometric expressions and doing proofs. Okay? The first one should not be a mystery to you at all. It is literally the Pythagorean theorem applied to the unit circle. Sine squared theta plus cosine squared theta equals 1. Radius is 1. Sine theta represents the y value. Cosine theta is the x value. So x squared plus y squared equals r squared. It is the basic equation of a circle. But remember that we can rewrite these Pythagorean identities. We could change the order around a little bit. Like let's say we wanted to solve for sine squared theta. So I would have sine squared theta equals 1 minus cosine squared theta, right? I just moved the cosine squared to the other side. What if I wanted to solve for cosine squared theta? Same thing. Move sine over to the other side. 1 minus sine squared theta. There are even more ways to do this. I could have chosen to subtract the 1 and then subtract the other one. So I could have written, say, sine squared theta minus 1 equals negative cosine squared theta. You have to be familiar and comfortable with taking these Pythagorean identities and rewriting them into whatever form fits our need at the time. Okay, now how did I get this next one? Where did 1 plus tangent squared theta equals secant squared theta even come from? Believe it or not, I took the original Pythagorean identity and I divided everything by cosine theta. So to get over to here, we're going to divide by cosine squared theta. Think about it. If I do sine squared theta divided by cosine squared theta, what do I get? I get tangent squared theta right there. And if I take cosine squared theta and divide it with cosine squared theta, I get 1. And then when I take 1 and divide it with cosine squared theta, I get secant squared theta. This particular worksheet just put the 1 first. I'm used to writing this particular identity as tangent squared theta plus 1 equals secant squared theta. It doesn't matter. Again, we could solve for different things here. We could get the 1 by itself. We could say 1 equals secant squared theta minus tangent squared theta. We could even have solved for tangent. Clean up that secant just a little bit there. Made it worse. Oh well. Tangent squared theta. What is tangent squared theta equal to? It's equal to secant squared theta minus 1. Okay. How did I get the last one? Well, I took again the original identity, but this time I divided by sine squared theta. That looks terrible. So So when I do sine squared theta divided by sine squared theta, I get 1. When I do cosine squared theta divided by sine squared theta, I get cotangent squared theta. And when I do 1 divided by sine squared theta, I get cosecant squared theta. Again, you could rewrite these to your heart's content to suit whatever need you happen to have. And cotangent squared theta would equal cosecant squared theta, subtract 1. These are your fundamental identities. Learn them, memorize them, become comfortable with them. Okay, for the next section here, I am going to scroll down and evaluate some of these functions. And if you look at them, the first thing you probably notice is, Miss Mullen, didn't we already do this? Didn't we just take a test on this stuff? Well, the answer to that is both yes and no. We did already do this, trig at any angle, no problems. But now what I want to do is look at it through a different lens. Can we use the identities that we just did up above to evaluate these functions, to figure out all 6 ratios? The answer is absolutely yes, we can. So I'm going to work out the first one. I'll pause the video, ask you to try the second, and then I will provide answers for you so that you can check your work. So we're given cosine, and we're given the tangent is greater than 0. So we're being asked to find all 6 ratios. Let's see. Well, if we know that cosine is negative, but the tangent is positive, that must mean we're in quadrant number 3, because tangent's positive in the 3rd quadrant. Yeah, okay, so let me change this just for a moment. Sorry, we're in quadrant 3. What do I need? I need all 6 ratios, right? So I need sine of u, I need cosine of u. So maybe I can go ahead and make myself a little answer box over here. Sine of u, cosine of u, tangent of u, cosecant of u, secant of u, cotangent of u. Okay. My u's are a little too large. Sorry about that. We already know cosine, right? We know cosine is negative 2/3. Since we know that that one's negative 2/3, we also already know the secant. We just flip it over. So it's negative 3/2. How do I find the other ones? Well, you've got a couple different ways to approach this. Just use the identities from above. We know that sine squared plus cosine squared, sine squared of u plus cosine squared of u equals 1. So we could go ahead and plug that in and have fun times there. That would give us sine, which would give us cosecant. We still don't have tangent, though. Well, let's do it one step at a time. Let's go ahead and do that first piece that I just mentioned. We know that sine squared u plus cosine squared u equals 1. We know the value of we know the value of cosine squared u. We don't know sine squared u. Cosine squared is negative 2/3 squared. Okay? Negative 2/3 squared is 4/9. So we know the sine squared of u plus 4/9 equals 1. Sine squared u equals, I subtract the 4/9 over, so I'm left with 5/9. And when I square root both sides in order to solve for sine of u, I end up with sine of u equals the square root of 5 divided by 3. As the square root of 9 is 3, but the square root of 5 is irrational, so that's good enough. Hey, there's sine, right? I can go back over to my answers and say sine is radical 5/3. Ooh, give me one sec here. Hold on. Should this be positive or should this be negative? Well, I'm in quadrant 3, right? Sine's got to be negative. So let me go back and stick a negative up there in that fraction. Sweet. Oh, and since I know sine, I know cosecant, right? Just have to flip them over. But remember, you have to rationalize. So it is negative 3 radical 5 all over 5. Not bad. Still don't have tangent, still don't have cotangent. Ooh, but I do know that tangent of u is equal to the ratio of sine u over cosine u, right? So I'm going to say, all right, cool. Tangent of u equals sine u. You know what? Hold on a second. I'm going to rewrite this. I'm not leaving myself quite enough space. Tangent of u equals sine u over cosine u. What is the sine? Sine was negative square root of 5 over 3. Divided by, what was cosine? Negative 2/3. And again, this looks terrible, but remember, we know that since we're dividing a complex fraction where both denominators are the same, we're really only needing to look at this divided by this. Negative divided by a negative, of course, is positive, and so all I really have is divided by 2. Okay, so I can go back over here to tangent and say that is the radical 5 divided by 2. Cotangent, of course, is just the reciprocal of that. Ends up being 2 square roots of 5, all divided by 5. And there you have it. There's all 6 ratios. Going to give you a moment to try the one at the bottom. Do attempt to work it out. If you're just going to copy my answers, you may get your stamp on the homework, but you are robbing yourself of an opportunity to get some practice doing these substitutions. Alrighty, so here are the 6 answers. Notice how I wrote out cotangent first. I used the reciprocal identity to find the tangent value. I wrote out sine of x because it was also provided, and then I found that reciprocal value, which is cosecant of x. I then realized that since my cotangent was negative and my sine was positive, I was working in quadrant 2, which meant that my cosine and my secant ratios had to also be negative. And off to the side in green, you'll see that I chose to use the identity 1 plus tangent squared x equals secant squared x over the other one I used before. If I would have used sine squared x plus cosine squared x equals 1, I would have had to have taken the fraction radical 26 divided by 26, squared it, and then solved back for cosine. Definitely not the easiest math to do. It was much easier, as you can see here, to find the secant x first and then just use its reciprocal identity to get back to cosine. There you go. You know, I'm going to go back and insert one more little bitty thing since I have a moment and I am splitting this section up into 2 videos. I've noticed over the years that a lot of students, and I'm back up here, by the way, I'm right up in here looking at this. When you solve a square by square rooting both sides, many, if not most, students will forget to do this right there. Technically, when you're solving a quadratic and you're taking a square root, remember that both the positive and the negative root may be a solution. If you think about that, it makes perfect sense. Positive square root of 26 over 5 times itself would give you the radical 26 over 25, as would a negative square root over 5 times the negative square root of 26 over 5. You would get the exact same value. In our problem, in our red box, the only one I was interested in was the negative value. Since I was in quadrant 2, cosine has to be negative, and therefore so does secant. This is different than usual. Oftentimes in your previous math courses, you were interested in the principal root, which is the positive value only. But here you just need to remember that both of them are solutions, but for our purposes here and now, the negative one is the one we want. Later on at the end of this chapter, we will be solving trig functions, and had I not included my positive and negative sign in front of my square root of 26 over 5, I would have gotten half of the problem wrong. So I thought it was an excellent time to go back and insert that little tidbit of knowledge in. Thanks, guys. I'll see you in the next video.